We're good to go? Excellent. Good morning, everybody. We're getting towards the end of a very long week. I don't know about you all, but I'm looking forward to sleeping all weekend. Okay, informal survey before I get started. How many people here are intimately aware of opendaylight? Okay, intimately aware of the OVS ML2 driver in Neutron? And how many people are very familiar with OpenFlow 1.0, 1.3? Okay, and how many people here read the talk description and said this is a presentation for people who are not familiar with networking? Okay, so just to level set, the idea here is to give an overview of how things are today with the OVS ML2 presentation, ML2 mechanism. Give an overview of how they're different when you use opendaylight with, just to be precise, with the OVSDB netvert southbound interface of opendaylight, and why you would even want to use opendaylight. So since many of you seem to be familiar with opendaylight already, I'm gonna go pretty briefly here. But what is opendaylight? It's an SDN controller in the context of OpenStack. It provides network virtualization. It provides the ability to define a network topology for your virtual infrastructure, which is independent of the physical fabric, the underlay network. It is also a platform for network engineering. So one of the key audiences of and user bases and developer constituencies of the opendaylight project is people who are doing kind of advanced research on the network. Right? It gives you access to some very detailed and low-level information about what's going on the network and allows you to act on traffic that's going across the network. So opendaylight.org, I invite you all, if you aren't familiar with the project, to go and read more there. So that first one, what's an SDN controller? The idea is that you centrally define the way traffic flows across your network, and that policy, that central definition of the way the traffic flows is pushed to the edge and enforced on the edge by physical or virtual network devices, virtual switches, physical routers. opendaylight has a specificity that it manages multiple southbound interfaces. So it can talk to OpenFlow devices. It can talk to Open vSwitches via OpenFlow and OVSDB. It can handle netconf, and it can also handle, there are multiple mechanisms for integrating other network management protocols, device types, vendor plugins, and even handing off to other SDN controllers for part of your management. So one of the projects, for example, in the Helium release is a plugin for OpenContrail. There is VTN, which hands off to alternative network management pieces of infrastructure. So it manages multiple pieces on the southbound, and it can handle multiple protocols, L2, L3, and so on. So why would you use one? Well, a few sample applications, and I don't want to go very into detail, but the one I've mentioned already, network virtualization, is the one that's probably of the most interest to OpenStack users. But it also gives you the ability to interact with how your network interfaces with the WAN, right? So perhaps optimizing WAN traffic to ensure that a certain type of traffic gets a higher quality of service than let's say Skype or BitTorrent. Traffic engineering, identifying hotspots and routing around them on your network. This is getting quality of service information in real time from your network. These kinds of applications are the things that are enabled by an SDN controller. And also software-based network applications, the ability to do things like intrusion detection, intrusion prevention, DDoS protection, handling VPN as a service. All of these things are possible in an SDN controller because you've got direct access to your network traffic. Open Daylight has a lot of projects. This is the Open Daylight Helium release. The Lithium release, which is in final preparations now and is due for a release in about a month, has many more projects. Some of these projects have, in some sense, fallen by the wayside. But you can see there's a rough breakdown here of we have multiple northbound interfaces, multiple ways to interact with Open Daylight. We have multiple southbound interfaces that can handle multiple device types on the south. And then in the middle, we have a controller which understands the state of the network and has multiple network applications that can act on it. In the context of OVS DB managing Open vSwitch, the OVS DB project in Open Daylight, to be precise, these are the pieces that matter. So we've got an OpenStack Neutron northbound interface. We deal with Open Daylight via a northbound REST API. We have the ability to integrate AAA to make sure that authentication and authorization are consistent across Open Daylight and OpenStack. We have an OpenStack service which replicates what Neutron can do. OVSDB, the Neutron service which defines the network piece that talks to the OVSDB plugin southbound and the OpenFlow 1.3 plugin southbound. We'll get into all of the details of that a little bit later. The point here is there are, in the context of OpenStack, about half a dozen projects that are of particular importance. And the rest provide you the ability, by working with Open Daylight directly, to do more advanced features. But these are the projects that Neutron will deal with in the context of network virtualization alone. OK, so some of the core Open Daylight use cases. Open Daylight traditionally has had a big tent approach. But the Open Daylight board has recently said we want to focus on two specific zones as areas of focus. And one of them is OpenStack network virtualization. And there are multiple aspects to that. And the other one is service function chaining and the NFV use case, which you may have heard quite a bit about this week. NFV is a very hot topic. It's network function virtualization. It's the ability to migrate physical workloads to virtual machines in the context of telco applications, core packets, IMS, voice data, all of the things we're used to in telco services. They're currently physical machines and they're moving to VMs. And all of those things need very specific network constraints. They have very specific network constraints. So something like Open Daylight is required to enforce those constraints and to provide the ability for an application developer to define how that application is going to live on the network. So these are the core use cases that Open Daylight is focusing on. Things like SFC is service function chaining, the ability to chain multiple virtual machines together as network services on the way to. So when you get, for example, just to take one example, traffic comes into your network, you do some deep packet inspection on it, and you detect that it's a video flow, and you say, OK, let's go through the video bandwidth limiter because we don't want to use all of our bandwidth on video, and let's go through the parental control because we don't want kiddies watching porn, for example. And that would be a service chain which would have 3 nodes in it. And then finally, it gets to the endpoint. OK, so Open Daylight and OpenStack. So to start with, I promised a brief overview of how OpenStack works with just the Open vSwitch ML2 plugin. I don't want to go into too much detail here, but essentially, the ML2 mechanism replaced the Neutron plugin architecture, which was there before. The idea is that you've got the modular layer 2 plugin hands-off, defines, you have essentially 2 things, that the tunnel type between hosts, which can be VLAN, VXLAN, or GRE, the mechanism manager, and there are multiple mechanisms. Open Daylight is one of them. This is a way for Neutron to delegate certain operations to third parties. The way Neutron does it with the OVS plugin is that you have Neutron server receives an API call. It records. It actually sends out first the message to the queue. You've got one L2 agent. the Open vSwitch agent on each compute node, which is managing the flow table on your Open vSwitch instance on the compute node. We have an L3 agent per router that's created. The L3 agent, we'll get to what it does a little bit later. And we've got a DHCP agent per subnet, which has DHCP associated with it. Neutron passes on the request via the agents, gets a, OK, this is done, and records the change of state of the network in the Neutron database. This is a bottleneck here, potential bottleneck around the message queue, the scaling issue of L2 agents coordinating across multiple hosts. Anyway, so this is how traffic flows with OpenStack. So there are two things. There, how do we define the flow tables across the hosts, and then how does the actual traffic flow when we've defined them? So this is a pretty simple setup. We've got a compute node over here on the left, which has two VMs on it, and we've got the control node, Neutron control node here on the right, which has a DHCP agent and an L3 agent running on it, the purple boxes here. Okay, so this is all from Lars colleague, Kellogg Stedman, a colleague of mine in Red Hat, who has described everything here in very deep detail, and it's an awesome page. It's networking in too much detail. If you look for it, it's really good. This was huge education for me. So if we look at the first level, what happens from the instance? Well, we've got ETH0 on your Nova instance is connected to a tap device in the host namespace. That tap device is linked to a Linux bridge. That's where security rules, when you define your security rules associated with an instance, there is one of these per instance living on a compute node, and that's where there's a set of IP tables that say what's allowed for that instance, right? So we define a chain. There's the multiple chains that get defined. One for the, so you see the same hex string 7C7AE61E0, and then there are two tables that are defined, one for output, one for input, O and I, and they define just it's normal IP tables that is defined on that bridge, and some would say that's a bug. That really you should be able to do that in the Open vSwitch bridge. I'm not going to get into that debate today. Then we bridge from that Linux bridge down to an integration bridge, brint. And that's essentially where traffic from instances are tagged with VLANs. So the tenant that you're associated with, or the subnet that you're on, the network isolation is, the isolation of traffic from that VM is defined there. So just showing the vSwitch, OVS, VS controls show. You see the port, the QVO. So this is, you'll see the same hex string appearing throughout the chain, right? The 7C7 AE61E. I think that's got some significance to Neutron, but I don't know what it is. If you ask questions afterwards, I may defer to some people in the audience who know this stuff a lot better than I do. And we tag. So there's a tag 1. So you're tagging all of the traffic coming in here with VLAN ID 1. Then you get handed off to a tunnel, brtun. And that's where we do the tunneling between all of the hosts. So GRE, VXLAN, VLAN, whatever you defined in your ML2, not mechanism, the other one, type, tunnel type. And then it's sent to the physical NIC on the compute node and tunneled to the peer, whichever is the peer that you're peering to. So it's converted and then it gets to the other tunnel, and it's converted back from GRE back to VLAN, and we'll see how that happens. And then traffic sent with the appropriate VLAN tag back up to brint, right? So this is a flow table. What you can see here in red is if traffic arriving has a tunnel ID of 2, and its destination is broadcast. So if you're sending broadcast or multicast traffic from GRE tunnel 2, you're going to set mod VLAN VID. So we're going to set the VLAN VID to 1, and we're going to output that to port 1. So obviously somebody knows what the port 1 corresponds to where this should be going. If you look further down, if it's a tunnel ID 0.2 and it's going to a specific MAC address, then we modify the VLAN ID and send it back up to the BRInt. And if it's coming in from port 1 and the VLAN is 1, then we set the GRE tunnel to 2 and we send it off to the Ethernet card. So that's we get to BR-ton on the Neutron host, passes up to BR-int on the Neutron host, and we get that GRE to VLAN conversion in BR-ton, and the BR-int bridges to the Neutron agents, right? The DHCP agent, the L3 agent. So if we look at the BR-int, we see two tap devices here, tap F14, blah, blah, blah. That's got a VLAN tag 1, which is the same as on the other side, and tap C2D7DD, VLAN tag 1. So these are all associated with the same instance that we saw on the compute node. Each network with DHCP has subnet with DHCP has its own network namespace, and each router has its own namespace. So if we do an IPNetNS, we see a QDHCP namespace, and we see a QRouter namespace. And that's how we can allow multiple DHCP domains with overlapping IP addresses to exist on the same OpenStack cluster. And if we dig into the namespaces, for example, on this QDHCP, we see F14C, that corresponds to, remember, the one of the ports that we saw on the bridge. And this is essentially just a DNS mask process, right? Which is doing DHCP, and you can do a PS minus EF on the Neutron host, and you'll see the DNS mask process. You can grep for this F14C59 C598D, and you will see the process that corresponds to just that VLAN. On the routing side, we get to the router, which is essentially a set of routing tables, IP tables, and the traffic is sent on to BRX. So this is where we do the NATing that happens on BRX. So if you've got floating IPs, I think it's handled there. Correct me if I'm wrong. I'm right? Good. So the routing tables for the router are defined just with normal IP tables on the control host and in that namespace. So we've got two connections, QG, which is the gateway associated with the router, and QR, which is the router interface back to BR-int. If we look at the OVS-VS control, we see again interface C2D, tap C2D7, that corresponds to the C2D7, the router, QR. So we've matched up the router with the port it's on. Okay, so that's how it works with ML2. I don't know if anybody here learned anything there. I hope so. How does it work if you swap out ML2 and you put in OpenDaylight in its place? Well, first things first, how does Neutron talk to OpenDaylight? Well, we've got a single endpoint. So there's a common service northbound endpoint, which is configured as the API connection point when you do the mechanism. We'll see how that works a little bit later. That talks to the Neutron service. So there's Neutron ML2 talks to the OpenDaylight through the REST API. That talks to the Neutron service. It says, OK, I've got multiple, I need to handle this type of request. I'm talking to Open vSwitch. Can anybody handle Open vSwitch stuff? Can anybody do Open vSwitch? So we've got a request goes down to the OpenFlow plugin, which actually codes the flows, and we've got an OVSDB provider, which is listening southbound for events from the Open vSwitches via OVSDB server on the compute nodes. It simplifies things because you've got a single central control point, and you've got the ability to scale that out in all the ways that you can scale out OpenDaylight, yes. So how do you do it? First, install OpenStack. I would love to tell you something differently, but if you've already got OpenStack and you've got a bunch of networks and subnets and network configuration in place, there is not currently an easy way to migrate when you're migrating from the OVS ML2 plugin to opendaylight, so you need to sort of clean out your Neutron config and replay it once you've got opendaylight in place. You install your opendaylight. You can do it either on your Neutron control host if you want to have them both on the same host, or you can do it on a separate host. It's just an API endpoint. You can load balance that API endpoint if you're doing a cluster. You clean your OVS DB configuration on all of the hosts, and you do an Open vSwitch set manager command on each of the compute hosts to say, okay, this Open vSwitch is being managed by this host, this controller. And then in the OpenStack side, and we'll see the config, you set opendaylight as the ML2 provider, and then all of the Neutron commands are going to opendaylight, and all of the Open vSwitches are already attached to your opendaylight instance, and everything should just work. I see Flavio nodding his head, so I don't think I've said anything too wrong. Okay, step one, Neutron config. Unfortunately, no migration path, so you need to delete all your subnets, networks, routers, ports, stop the Neutron service, stop and disable all of the L2 agents on all of your compute nodes. But I think I mentioned that later. So installing opendaylight, there are a number of things that are required. Anybody who is intimately familiar with opendaylight will say, well, shouldn't this all be picked up by dependencies when I install just the ODL, OVSDB, OpenStack feature? And yes, it should. With Helium, it doesn't quite work that way, so you need to install a number of things. So the base is basic services. NSF is a kind of a catch-all basket for features, which includes, among other things, some of the Neutron northbound stuff. In Helium, and this will change in Lithium, ODL uses ADSAL, which is application-driven service abstraction layer. It's moving to MDSAL, model-driven service abstraction layer, which is essentially you define a Yang model for the service, and then that generates the north and southbound interfaces that it needs. The OVSDB OpenStack, OVSDB northbound. Why do we need OVSDB northbound? Yes, the OVSDB server is talking to the OVSDB plugin. OVSDB is kind of namespace overloaded here, because OVSDB is actually the database that manages the Open vSwitch configuration on the compute nodes, and a plugin to opendaylight, which manages the network and the southbound interface from OVSDB, the service, the network service, to the OVSDB on the switch. So it's got at least 3 different meanings depending on where you are. And Deluxe, this is just if you want to have the GUI. Deluxe is the daylight user experience. So it's the web-based UI for Helium and Lithium. Okay, so after step 2, if you go to, the slides will be online, you'll be able to get the URL, but it's essentially if you go to your opendaylight host, port 8181, you will see this. You've got opendaylight. It doesn't have any devices that it's connected to. This is what it looks like when opendaylight is installed correctly. Then, for each host, you stop and disable your Neutron Open vSwitch agent. You don't need it anymore. The L2 agent is going away, and you're going to replace it with just the normal OVSDB server. You stop your Open vSwitch service to clean out your local database. There are good instructions on this in the opendaylight wiki. You restart your Open vSwitch service, and you connect OVS, VS Control Set Manager, and you connect it to your, this IP address is just whatever your opendaylight control host is. You may need set enforce 0, and that's because this port is not open in the default SE Linux policy. It's better if you allow the port traffic, but consider this a bug that will be fixed. So after that, you've got an empty OVS VS control. You've got an empty Open vSwitch configuration, which shows that you've got your config is being managed by a manager. It's connected, and the bridge brint, we don't have any brton anymore. Brton goes away because all of the tunneling is done on the integration bridge. Is also being controlled by port 6633 and is also connected. And that's all you should see. If we look at the flows, and I've snipped here, but you've got this is an empty flow table. OVSDB sets up, it uses tables, open flow tables. So we've got table 0 corresponds, and there are semantics associated with what each of these tables does. So it's just table 0. You can see, yeah, so there's one thing there is that the controller is connected on table 0. So this is, it allows, or there will be open flow traffic across that. That's essentially what that means. We'll see what each of these tables mean here later, but the idea is it's kind of a flow table where semantically packets are coming in, they're handled with table 0, then they're sent to table 20, sent to table 10 to 30, and so on. That's the way it works. So this is what you should be seeing if your Open vSwitches are correctly connected to your controller. Then you configure Neutron. So there's an init file. You just say the mechanism, you set it to Open Daylight, your tenant network types VLAN, and this is the API endpoint, so ODL control, whatever the ODL control host is, port 8080 controller NB v2 Neutron. That's just the API endpoint that's exposed by Open Daylight. And so you're done. We can stop now. So going back to the networking in too much detail, what does the same thing look like with Open Daylight? Well, the only thing that's changed materially is that we don't have that BR ton anymore. There's another thing that may change. You may, especially with Lithium, no longer have an L3 agent, and you may end up having your BRX on each host and having the routing handled directly by Open Daylight on the BRInt. We'll get to a little bit about that later, but that's not the case with Helium, which is what I used as my reference here. So it's essentially the same thing, right? So why would you use it? But let's see how the flows look like. So we've got, if we look at the bridge on, this would be a compute node. We see there's a VXLAN that gets created, so it's peering the compute node to the control node. If we have multiple compute nodes, it will peer to them too. So you'll see an interface, a VXLAN, which will bridge to each node, physical node on your OpenStack instance. And we've got a couple of ports here. Those are going to correspond to your instances. If we look at so this is list interfaces, just to get some ideas of the kinds of information that you need or that you have in open flow. So let's look at list interface, and external IDs is an important one because this is what allows you to associate a MAC address and an OpenFlow port with a specific UUID, which is the port UUID in Neutron. So that's what allows OVSDB in Open Daylight to make the connection between the virtual port in Neutron and the physical port on the vSwitch. And also the interface, so you can see the actual tap device there as well. If we look at the flow tables, so this is, the first thing here is if traffic is coming in on port 3 and its destination is this MAC address, which is, for want of a better, 7595 at the end, then set the tunnel to 0x3A, so it's setting the VLAN or VXLAN ID. If the traffic is tagged with, so later that's table 0. Table 0 is where all of the tagging gets done. Table 70, which is L2 routing, or L3, it's part of L3, is if your destination is the IP address, then set the destination MAC address to 7595. So it's doing essentially a reverse ARP lookup. And the last rule here, table 110, is the actual L2 routing. If your tunnel ID is 0x3EA and your destination MAC address is 7595, then you send it out to port 3, which we saw earlier. So that's how traffic is routed to and from the instance. If we look at, there are some rules in the and this is just, I've selected, because if you looked at the flow table, it would be, oh yes, there's a 70-line flow table. and I can't read it because the text is too small. So I've extracted some of the key lines here to just to give you an idea of the kinds of things that happen in the flows. So here, if we're sending out broadcast traffic and it's on tunnel ID 0x39, if it's local, then we send it to output to port 2 and to port 1. So we're going to send it to the instance that's attached and over the VXLAN bridge. And if it's remote, then we just send it over the VXLAN bridge. Is that right? Okay. And then finally, this is one of the things that's kind of cool. Table 110, the ARP. Okay, so if it's if the tunnel ID is 0x3A, so this is all of the instances in that group of instances, that subnet, and the destination MAC address is either of the instances on the other compute node, then it'll be sent over the tunnel. So this is it basically it says, okay, if you're going to MAC address whatever, then I'll send you to the right port. And each of these compute nodes is coded with the correct complete ARP table for your network. One of the things that's kind of cool is distributed ARP. So you don't get any ARP traffic on the backplane because what happens is, because every compute node has a complete ARP table of your network, whenever an ARP request comes in on any port, you can say, well, I know where that guy is. So you just swap some fields around, and you can do all of this with OpenFlow tables. You say, okay, I'm going to move field 1 to field 2, move field 3 to field 4, and then I'm going to set this value in field 1 and field 3, and I'm going to just send the packet back on the same port I got it in from, which is kind of cool. It's one of the nice things. Okay. So that's where we are with Helium. Coming in Lithium, so this is the OVSDB project in opendaylight. Have been hard at work migrating from ADCell to MDCell. I mentioned that. That's a big chunk of work. So that's going to enable, there are some historical reasons why we had both. The general decision of the community is that everything should be MDCell from here on. And so a lot of the ADCell legacy projects are migrating to MDCell. There is an aim for feature parity with Neutron, so all of the features that are currently available in Neutron should be available directly and provided by opendaylight, including load balancing as a service. And currently the east-west is working and the north-south is not finished, but the idea is to have native DVR. So essentially, every compute node will have the ability to route traffic directly. So you've got a native distributed virtual router using just OpenFlow on the compute nodes, controlled by the controller. And the Neutron northbound interface has been split out from the opendaylight controller. And I'm done. So I hope that was educational. I have about 7 minutes for questions. Do we want to get people behind the mic, or will I just repeat the questions? Maybe it's just easiest if I repeat the questions. Okay, you, and then you.
Thank you. I know that you did talk about migration, but you say it's unfortunate that there's no migration. But are there any plans in the community to help people migrate from OVS back into ODL backend, because they can't just go delete hundreds of networks and download the code?
So the question was, I know that it's currently not possible to migrate from OVS to ODL without dropping the entire config. Are there plans to enable that? Because it makes it hard to move to ODL if you have to drop everything. I am going to defer to Ed. Ed, are there any plans to do that? To enable, so I guess the idea would be to have ODL read your network config and reconfigure the vSwitch using ODL instead, and so allow people to keep their Neutron config and just reflect that Neutron config in an ODL config. Like, enable migration from OVS to ODL more easily. That should be a doable thing, he said.
So I think I've got 2 questions. One of them was going to be, you looked at OVS for but the other one actually I've just come to is, what about scalability in the size of these Mac data?
Right.
The idea of putting every single Mac with every single possible endpoint
So there were two questions. One is, what about oven? I don't know the answer to that, but Flavio does. And the second is, isn't having the entire ARP table on each compute node a scaling issue? And I don't know the answer to that either. Okay, so Flavio says what Oven will do is roughly the same as what opendaylight does, but it's just co-located with OVS, so it's moving things a little bit closer to the edge. But Oven's an accelerated data plane. I'm going to suggest that you take this conversation offline. I'm feeling a bit weird repeating. Yes?
Is security groups actually supported in ODL?
Question is, so you had the mic, so I don't have to repeat the question. I don't know. Are security groups supported in ODL? Are there plans to do that? There are plans to do that, but it's not supported right now.
Okay. And then the north-south for the north-south routing, right? Like internal network to external network. For that, the natting is actually done using the OVS rules in the BREX, or
so the question is in north-south routing. Oh,
yeah,
the mic. I don't know. I'm sorry. So it's newer development. I'm going to defer again to Flavio. Is the natting done in with the open vSwitch tables on each? It's with installed OpenFlow rules on the compute nodes.
Okay, thanks.
Yes, I'm going to take this question before I take you, and then that's, I think, going to be it.
You said the last slide said feature parity with Neutron.
Uh-huh.
But in which Neutron, which release of Neutron features are you at parity with?
Okay, so the question is feature parity with Neutron, which version of Neutron? I'm deferring to my colleague who's... Okay, I'm sorry. I don't know the answer to that.
And you said feature parity, but you just said security groups were not supported.
So security groups are still supported on the instance, but what happens is that, so there is an issue with Open vSwitch, having IP tables applying to an Open vSwitch instance. I don't know if that's been fixed or if there are plans to enable that. So you still need the Linux bridge there, but I mean that's created by Neutron or libvirt. I don't know, one of them. With 2.4 and connection tracking, we might not need the Linux bridge. And then last question, I'm afraid.
Yeah, on the command to set the controller as the manager, I think it was set manager.
Yep.
That's a CLI command right now. Is there any plans to make it more dynamic, like put in a configuration file? And if so, do you have any thoughts on which configuration, like the ML2 plugin in it?
I'm really not the best person to talk to about that. The question. So, are there plans to? That was one of the questions I had is can I not just sort of register a new compute node somewhere and have that automatically connect to the controller? Maybe that's part of the system management, whatever system management layer you're using to manage your OpenStack installer would take care of that. I don't know. Okay, thank you all, and enjoy the rest of the conference.